Hi students, welcome to the continuation of Chapter 5. Again, I'd like to strongly emphasize to all of you that I would recommend that you have handy your online textbook and also our good familiar periodic table. Fancy technology once again coming through. But anyway, I think that those will help. Again, I apologize for the fact that I'm not tech literate, but we're going to get there. Anyway, I've decided that section 5-3, being that it is so long, that I'm going to break it up into 3 parts. This is 5-3 part 1. It begins with Roman numeral 3 on your notes and should also be labeled Notes Part 1. Alright, the electron configuration and periodic properties. Under A, atomic radii is number 1, size of an atom. Under A, it is defined by the edge of its orbitals, O-R-B-I-T-A-L, or orbital. B, it is the fuzzy, F-U-Z-Z-Y, and varies under different conditions. Under C, atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded, and you need to take a look at figure 5-12 out of your online textbook. Number 2, periodic trends. This refers to figures 5-13 and 5-14. A trend to smaller atoms across a period is caused by increasing positive charge of the nucleus that gradually pulls electrons closer to more highly charged nucleus, more protons. Under B, attraction of the nucleus is offset by repulsion among increased numbers of electrons in the same outer energy level. Number 3, group trends. A, in general, the atomic radii of main group elements increase down a group. B, Ga, gallium radii, is less than aluminum due to filling of the 4th main energy level is outweighed by a shrinking of the electron cloud caused by a nuclear charge that is considerably higher than that of aluminum. Number 4, we are going to do sample problem 5-5. I would like you to take a look at that on your online textbook and take a few moments to solve it. It's basically is a prediction as to which of the following list of elements has the largest atomic radius. Then we're going to go over this in class when it comes time for us to meet. And then we're also going to be doing number 5, practice. The next part of this lecture covers B, ionization energy. And again, I would like to refer you to figure 5-15 and 5-16 out of your online textbook. Number 1, A plus energy yields A plus an electron. The electron can be removed if enough energy is supplied. Number 2, and this is an important definition, ion, I-O-N, is an atom or a group of bounded atoms that has a positive or negative charge. And we're going to talk about this later in some of our chapters that will be coming up. We'll be emphasizing ions. Number 3, ionization is any process that results in formation of an ion. Number 4, ionization energy, which is usually abbreviated IE. Ionization energy, or first ionization energy, is the energy required to remove one electron from a neutral atom of an element. Now there was a technical glitch. From a neutral atom of an element. Number 5, period trends. Under A, group 1 metals have the lowest first ionization energies. They lose electrons most easily due to that is the major reason for their high reactivity. In other words, it's pretty easy to snatch an electron away from a group 1 element. B, group 18 has the highest ionization energies. They do not lose electrons easily, and this is what causes their low reactivity. That's why they're a noble gas. They're already stable. They don't want to lose any more electrons. Under C, in general, ionization energies of the main group elements increase across each period due to increasing nuclear charge. Under D, in general, non-metals have higher ionization energies than metals do. Number 6, group trends of ionization energy. Under A, among the main group elements, ionization energies generally decrease down the groups due to each succeeding element has higher energy levels further from the nucleus and the ionizing energy removed more easily. So in other words, the bigger the electron cloud, the easier it's going to be to snatch electrons away. Under B, also more electrons lie between the nucleus and the highest energy levels, which shields the outer electrons from the effect of nuclear charge. Both influences overcome attraction of electrons to increasing nuclear charge. All right, number 7. Removing electrons from positive ions, table 5-3 out of your online textbook. Under A, second ionization energy, or what is called IE2, and third ionization energy, which is called IE3, the removing of additional electrons from positive ions. Under B, the second ionization energy is greater than or equal to the first ionization energy. The third ionization energy is greater than or equal to the second ionization energy, etc. C, successive ionization increases due to fewer electrons remain within the atom to shield the attractive force of the nucleus. D, thus each successive electron removed from an ion feels an increasingly stronger effective nuclear charge. The nuclear charge minus the electron shielding. Under E, special stability of noble gas configuration also applies to ions that have noble gas configuration. F, jump in ionization energy occurs when an ion assumes a noble gas configuration. These stabilities are indicated in blue highlighted numbers on table 5-3 out of your online textbook. In other words, if I take one electron away from group 1, it now has the same configuration as a noble gas. If I take 2 electrons away from group 2 elements, they now assume a noble gas configuration, and now it's going to be tougher to yank off the 3rd and 4th ones because they like that stable configuration. Under number 8, I would like you to take a look at the sample problem 5-6, and which is more likely to be in the S or P block, and which is more likely to form a positive ion. And then take a look at the practice problems for number 9. We will do these again in class on the board, and we will give you a few other examples when that time comes about. Anyway, this is my end of this lecture, 5-3. Part 1, and I hope you have a great day or evening.